Yeah. Yes. Yeah. That's the one, right? That's good. It's rather I don't. Sure. Sure. I spent last year. I spent about 5 hours
Works?
What we're going to eat, but
Is working? Great. Good. Just a question. The microphone is only for the recording, or? I'm not. It's not too, okay. But then I just know that I have to talk a bit louder. That's. Please tell me if anything, if I write too small or if I'm not loud enough. So hello everyone. I'm the other Lidia, as you probably know. Today we are looking at two main topics in the exercise class, which are covered in the exercise sheet. So with these, you should be able to solve the exercise sheet. And more in particular, maybe some of them you already saw, but we are just doing a recap. I hope it's not too boring for you, but I know that are exactly two topics which usually cause quite a lot of struggles. So please, yeah, interrupt me anytime. Tell me if I'm doing something wrong, which is can happen at any time. We start with matrix exponential. So what's the idea behind? You will see it, or you saw already probably that in exercise sheet 3, exercise 1 is about property of matrix exponentials. What does it have to do with quantum mechanics? So first of all, or one of the approach, if we look at the Schrödinger's equation, you derived in the lecture that this has the form like this, yeah, okay, time the derivative of our state. And here you can see that we have kind of like a correspondence to x equal to d times dt, here another constant of x. So it's not the same, absolutely. Here we have a matrix, a state, a quantum state. Here I see that A, B, x in R. But why am I showing you this? Because probably most of you have already solved the differential equations. Okay, and here we know that the solution here is like that x is proportional to the AE of something. This is the solution. Okay? So what are we doing now? Here we say that for special condition, for a special case, where the Hamiltonian, actually here I can put a t, a time dependence, but if the Hamiltonian is time independent, then we write the state, the solution of the state is a unitary transformation times C of t with is unitary of the form e to the minus h our Hamiltonian. Okay, so here we have exactly like this is why I show you this analogy, e to the exponential a matrix. Is this clear? Yeah, you'll show this in the class. Yeah. X proportional to e to the at something. This is proportional. This you means okay. So this is like so. If x is equal to epsilon, then we write that x is proportional to epsilon. This means in front of here we have a constant. If we would have x is equal, I don't know, epsilon square to epsilon square, then x is proportional to epsilon square, but not to epsilon. Is it okay? It's like maybe the symbol is like it scales like. Okay. Yes.
What would happen with x equals to y squared plus y?
Then then you cannot write such a relation. Yeah, this is like a 2 epsilon square plus y, something like this. Yeah. In case so for epsilon greater than what, like epsilon to infinity. In some cases you can say this is like way smaller. So you could write x is proportional to epsilon square. But in general, there is no, yeah. Cannot. Yes?
Sorry, what does it say there? U and then e to the power of?
Yeah, so minus I, maybe I write, divided by this h bar times my Hamiltonian, the matrix. Yes?
Just a question.
Yeah.
Why does our wave function directly equal to itself at the same time?
So, sorry. Yeah, that's a good question. Yeah, this is the problem of all quantum mechanics. That we have a nice equation, but it's self-consistent. So the variable appears on left and right. Okay? And this, I mean, that's something basically, I don't know how many thousands of researchers are finding ways of solving this equation in multiple ways. If we can solve this, then our work is amazing. Yes?
I have 2 questions.
Yeah.
So what's the symbol after E? Yes.
Yeah.
Symbol after E.
This is again, sorry, it's proportional. Yeah, maybe you saw it with this, but let's stick. I'll do my best to do proportional too. Into the denominator, yeah. So this is, I leave it like that because you see it everywhere. So if you write like this means that only this variable is divided by. And then what follows is afterwards. If you have multiple variables, let's see e to the x divided by ab, then you put brackets, okay? And yeah, so this that's good that you ask because I think that's like all quantum mechanics uses this notation. Yeah? And maybe sometimes you see E divided by H bar H, maybe. But it's, yeah, also with LaTeX, it's not that elegant. Then the E and H bar becomes very small. So I'll try to erase what doesn't matter here. So that we are, yeah. I hope, yeah, it's clear enough. So as you see here, you have E to a matrix, E exponential a matrix. So now we are looking at what does this mean? Maybe some of you have saw it already, but yeah, I guess a repetition is good anyway. So the question is, what is E to H with H A, sorry, a matrix? Yeah. So now we start, so like the definition is, let's start it easier. So suppose we have a number, a real number, or a complex number. Now let's make it with a real. And what is E to the A? Does anyone know the some? There are multiple forms to tell it. Yes.
It's basically the limit of 1 plus 1 over.
Yeah, that's correct. Yeah.
Of 1 plus
Yeah.
A over N.
That's perfect. That's perfect. Yeah. This is probably a form some of you already saw. And then there is another representation. Anyone of you knows? Yes? Almost, yeah, the infinite sum over what?
A to the power from N equals 0.
That's perfect, yeah. To infinity, as you said earlier.
And it's A to the power of N.
That's perfect, yeah.
Divided to N.
That's perfect.
And
yeah, this is correct. Or did you wanted to add something? Okay, so this is for real numbers. So this is my real number. And now we move to matrices. So a matrix. How we define it with the corresponding definition of this. But in this case, my capital A is just a matrix, a square matrix. This is actually important. Now I don't know which definition you saw, but in some cases you write like this. This is the number of rows and this is the number of columns. Then this depends a little bit of the teacher, but this is like square matrix. And if anything is unclear, stop me. But here we have then E to the A is equal the infinite sum of E, A, N divided by N factorial. Okay. What is N? So with A, capital A of N is nothing else than I times A, so matrix multiplication N times. Any question? So here it would be really E to the A is equal A, one, the identity, because A, this is a convention, A of 0 is equal the identity. Okay, the matrix like a real number, exactly the same. So if I take this sum, I put N equals 0, I will have A of 0 is the identity divided by 0 factorial. This is 1, the convention. You probably learned it a couple of years ago, or maybe even 1 year ago. And then we come to the second term. So we have n equal 1, a to the 1 is a divided by 1 factorial, which is 1. So plus a plus what is the second term? Yes? Perfect, yeah. 1/2 times a square, and so on. Okay. Is anything unclear? So now we are looking a little bit, okay, this is an infinite sum over a multiplication of matrices. And as you probably know, multiplication of matrices takes a little bit of time. It's easy computation, but takes a little bit of time. How can we then deal with it? Or what can we tell about the properties of this exponential? Okay. So now we move to the properties. And for this, we go first back to real numbers and remember one of the properties of these numbers. So for two real numbers, actually this is also complex, is exactly the same. Yeah, I can also write like this. It's absolutely great. So we have that e to the a plus b. Any of you knows how we can rewrite it or what's equivalent to? Yes? Perfect, yeah. E to the a, e to the b. And this is something now we use, or probably, yeah, if we saw it, we can write it like that without problems. We don't have to show it. I think that some of you show a proof, and we are now going through it. Not because we will ever ask you to do it in the exam. You can use this, of course, without derivations, but because it will help you solving the exercise 1a, where A and B will be capital letters, and there are not numbers anymore, but matrices. Okay, so we see. So we start with a to the a plus b, and we use our infinite sum here, this form, and we write like this. This is n equals 0, the sum over all of the terms, a plus b power of n divided by n factorial. Okay, so now how can we proceed? Anyone of you has an idea? Yes?
We can use the fact that we know that the sum is okay. Basically, we can use the, if I remember correctly, we would use the binomial theorem or something.
Perfect. Yeah, exactly. This is, and I will now show. If you haven't heard about it, don't worry. It's absolutely not a problem. That's why we are looking at it. I put it 1 over n factorial, and then here I use the binomial theorem. What tells the binomial theorem? The binomial theorem tells that a plus b to the n is equal to the sum from k to 0 to till n of n k, and this is the binomial coefficient. We will define this in a minute. A to the k, b to the n minus k. Okay, and this is for every n a natural number. Okay, we won't derive this. Of course, there is also a proof for it, but now this we use. And what is the binomial coefficient? This is very used in probability theory. This you write as n factorial divided by k factorial times n minus k factorial. And here I can put a box. Any question about the binomial theorem? Now I use this and I input it for every term. So these every term here I use here. This means I can just input this relation and I will get here a sum from k equals 0 to infinity of n factorial divided by k factorial times n minus k factorial, a to the k, b to the n minus k. And here, sorry, I put a line to separate this. Okay, is anything unclear? Yes? Ooh, that's great. This is a mistake. Yeah. Yeah.
Why can we use
yeah, you mean, so this is a natural number, and it's, yeah, this, I mean, these sums means kind of the sum over all natural numbers. Okay, so it's like a not very mathematical correct way to do, but this is, yeah, like we all, this is actually true because even mathematicians write like that, but this would be more correct, would be like that. Yeah, okay, but we always write it like this, but good point, yeah. That's, yeah. Great. So what we are doing now, we simplify this n factorial because it appears twice. Yeah. And now I realize that my k are not very clear. Yeah, great. And then we write it like this, n equals 0 to infinity of 1 over, let's write it like this, a of k divided by k factorial times b to the n minus k divided by n minus k factorial. So we are still similar. So maybe now we start to see that maybe the real, that is absolutely correct. Thank you. So k equals 0 to n. So now we use another trick, which probably many of you saw but forgot. Say, yeah, it's not something that we use in as physicists in our everyday life. This is the Cauchy's product form. Yeah, and what does it tell? I'll tell you, if any one of you knows, that's very great. I used to know it on my first year, and then probably I forgot about even the existence of this. It's the multiplication of two, what's the Ryan, what's the series, thank you, yeah. The multiplication of two series is equal, then there are some convergence criteria, but here we are not mathematicians anymore. We just tell that this is true. Okay, I think the two of them has to converge, otherwise this is doesn't hold. And we know about this coefficient, which is very powerful. The Cn coefficient is the sum from k equals 0 to n of ak times b n minus k. Okay, so this is another box we just used. And what we see here, we can write ak. Okay, now I wrote a bit, let's write it here with a tilde on top of it, so it's very clear. I write my ak tilde as a to the k divided k factorial, and my b n minus k tilde as b to the n minus k divided by n minus k factorial. Okay, is that clear? So what can I see here? This is exactly this. This is exactly this. I can use this product form in the reverse way. And I can write it as a sum, as the product of the two series. This means we have n equals 0 to infinity of n of a divided by n factorial times n equals 0 to infinity of b of n divided by n factorial. And what is this? Or how can I rewrite this? Anyone has an idea? This is exactly my e to the a, and this is exactly my e to the b, per definition. Okay, do you agree? This is the starting form. So sorry for this long mathematical derivation. This is not exactly what we usually do, but it will help you for the exercise. And it's also great, yeah, to keep in mind, especially these two theorem or product form. So now we go back to matrices. And so A, B square matrices. We have, let's suppose we have a sum over two matrices. The idea would be like writing, okay, this is A times e to the b. Okay, but this is unfortunately or fortunately not true. Why? The idea is like, so e to the b of square is equal, so yeah, let's write like this straight away, is equal a square plus ab plus ba plus b square. And from the previous lecture and exercise sheet, so in general, AB is not always equal BA. Okay, this we saw in the lecture and exercise sheet as well. Okay, this means this we cannot write as AB plus 2AB plus B squared. And why am I telling you this? Because in the Cauchy products form, if you see, it's a sum over always the A is always in front. And the B comes always after in the product. Why is this possible? Because AB equal BA for numbers, for complex numbers. Okay? So here I also have A plus B is equal A squared plus, so yeah, here I can write this. And this is exactly the form I obtain here. If I put this here, I have this, I cannot write it like that. Is this point clear? And please tell me, because it's actually a quite, not really nice feature of quantum mechanics, because everything gets way more complicated, but that's also why quantum mechanics is excited. Yes? No, no, it's true for commutative matrices. So yeah, and actually this is the exercise. Yeah, it's like exercise is show for AB equal BA relation holds. So yes, then it's actually time for a break. So let's reconvene in 10 minutes, and then I wasn't used. I will show you still one property of diagonal of matrices. It will be way faster than now, and afterwards we will look a little bit at tensor products. Yeah, and I'm here if you have any question.
No. No. What about what? Yes, exactly. Cool.
Now the problem is calculation of e to the a. So this beast, which is an infinite sum of a product of matrices. So what the problem is the infinite sum of matrices and the good news, of course I always put in because it's not exactly a problem and it's not exactly, or it's half good news, is that for diagonal matrix we know the exponential, or we can calculate it very easily. I'm not doing it right now, but if any of you wants to know, you can come later. The exponential is basically every element of the diagonal matrix exponentiated. So this is the diagonal of e exponential of alpha 1, exponential on alpha 2, and so on. Yes?
Generally speaking, whenever we have dense matrices or these
Right or sparse, it depends on how big the problem is. If it's a 4-qubit system, then you can be very dense. If it's 100, then they are mostly sparse. Yeah. So this is also something which helps us a lot, but not always, because even with sparse matrices it can be. But of course, with computationally, it's definitely better. Yeah. So how can this help us? And I have to go to the second one. So this is a special case. And then we have a bit of less special case. Because of course, not all of the matrices are diagonal. And this is with A is diagonalizable. If A satisfies this property, then we can write A equal U d U minus 1 with D is diagonal and U is unitary. And U is a matrix. So how does this is a property from linear algebra? We are not just proving it because fortunately we are not in linear algebra anymore. And how does this help us? So it follows that A squared will be then U times D times U minus 1 times U times D times U1 minus 1. And why does it help us? This is the identity matrix. So this will be U times D squared U minus 1. Is it clear? What will be for A to the N? Exactly the same. If we multiply E here times U times D times U minus 1, we will re-get the identity here. And so on. So these will be exactly U D to the N U minus 1. Is it clear? Great. So how can we go on with it? So follow up, or like a Koch recipe, let's say it like this. I always like this German word. It's like one, diagonalize your matrix. Two, exponentiate, so d to the n is equal so use this property. And three, like multiply e to the a is equal u times d to the n times u minus 1. So as yes, it's a very small example, I can show you that with x equal 0, oh sorry, a actually, a is equal 0, 1, 1, 0. If we diagonalize this matrix, which we are not doing right now, because yeah, we are not anymore in linear algebra, but I'll just show you very, very quickly without too many derivation. And these are also things that like you can input in linear, in Wolfram alpha, for example. So no scientist has to do it by hand. Yes? Yeah.
First, why is the second step? Why do the exponential?
So, sorry, so, okay, yeah, this is x from d, thank you, this is a mistake. So we calculate x of d, and here is, yeah, absolutely correct. I skipped one step and then, yeah.
Finally, if we multiply, because e to a, if we do this kind of trick, this calculation, then if u and u minus 1,
yeah,
because if we, okay, basically if we do a, we basically diagonalize it and we have e to the power of u times e times u minus 1. Do the u and the thing.
Okay, so the fact is then we have, okay, yeah, yeah. Then we have, so e to the h will be a sum from n equals 0 to infinity of u times d to the n, let's write it like this, u minus 1 over n factorial of n. And then we input our result here. So this will be the sum over n equals 0 to infinity of u times d to the n u minus 1 divided by n factorial. Okay, here I input this. And then I can, these are constant, I can put them out of the sum. So this is the sum from n equals 0 to infinity of u, sorry, I wanted to put it out like this, d to the n divided by n factorial times u to the minus 1. Yeah, thank you. And this is done the exponential of d. Okay. Yes.
Just to make sure, u doesn't have to be unitary, right?
No, this is, oh my God, what were the properties? No, I think that if A is unitary, then U is unitary. Yes, yeah, some people, Lidia, you know, or if A is unitary, then U is unitary for this property, if you diagonalize a matrix.
I was just wondering because
you
wrote u and u is unitary.
Yeah, that's exactly, yeah. And then, yeah, so this is a good point. Actually, for a unitary, for U is unitary. Yeah. Or even normal, yeah, normal. And then this means that U of minus A is equal U dagger. And we write like this is, we write it with a W, or in the course, as far as I saw, for this special case, we write it, then U is a W, this matrix. But Yeah, it's just a name, but I think in the exercise, B or C, it's unitary, and we write it with a W. Yeah.
Sorry, what does it mean for ADP?
Wait, it. So for unitary, I'm sure.
If A W equals A W A, then it's normal.
Okay. Thank you. Yeah. And then a dagger equal identity unitary. Yeah. In the case we have a unitary matrix U, then we write it, or in the exercise sheet is written as a V. Okay, if U satisfies this relation, but of course if you write it with a U is absolutely not a problem. It's just to tell you if you see this W, it's exactly because it satisfies this property, but it's also just written in the exercise. Okay, anything else? So yeah, for this matrix A, which is actually the X gate, as you probably saw, if we diagonalize, we obtain these three matrices. So this will be, yeah, step one. Step two will be exponential of D is then e to the -1, 0, 0, and e to the 1. Because of the properties we saw before. And three, we multiply -1, 1, 1, 1, -1, 0, 0, 1, -1/2, 1/2, 1/2, and 1/2. And this you can do within 1 minute. So the big part is diagonalized matrix, which for 2 by 2 is okay. But for bigger matrices, it gets impossible. Yes?
So why did you write down e to the power of?
Yes?
Like what?
This, you mean?
No, above it. That one, yes, like what, like, why? I mean, I get what it's standing around.
Yeah, so we are in the special case where U is diagonalized. This means we can write A like this. Now I want to calculate E to a matrix, and this will be, so we saw before that the definition is infinity e to the n divided by n factorial. So instead of A, I put on this form here, okay? And then what is not clear?
No. Can you maybe explain like why that's inside the exponential? No, I can't.
Then we use this property here, and then these don't depend of n, or are kind of pre-coefficients, so I put them outside of the sum, and then here I see that I have the exponential of my matrix. Really? Or you can come later.
Never mistaken the first step. So you say U exponential minus 3, there's the exponential, so the first step.
Here?
No, the actual example, right?
Yes.
That like where you finish now?
Yeah, this is e to the minus. Thank you very much. Yeah. This is, oh, yeah. Okay. Great. And yeah, this is we're not doing, but I'm sure you are able to. Oh my God, now I'm other small people. I know, yeah, exponential matrices usually are kind of, everyone is very scared of. Don't worry. I hope that with this introduction is quite long for one exercise, but I think it's important that once for all you see it, and yeah, of course, then you remember the properties which you will show in the exercise. And then, yeah, it's not that in our everyday life we start diagonalizing matrices and doing matrices multiplication. It's probably, yeah, maybe you won't do it that much or maybe not at all, but it's important to know how it works behind. So yes, now I have to decide just what to do. We move to the tensor product. And exercise 2 is about order dependence. And with the basis of tensor product and projective measurements, you can solve both exercise 2 and 3. So what's the idea? Quick recap. Yes. Yeah.
Just possibly this like a real number security that a of a plus b plus each of a plus b.
Yeah.
And said in general that's not true for matrices. Now if I know that let's say I have a set of matrices, or just two matrices A, B, and I find matrix U such that U times U times A times U inverse equals U times B times U inverse. That is, we find matrix U that.
So you mean, so A is equal U J U and B is equal U J D dagger U minus 1. Yeah.
Can we now say that they commute and then
so
we can produce actually.
Exactly. Yeah. Yeah. Exactly. Yeah. Mm-hmm. Yeah. Because you see. Yeah. Yeah. If they don't commute, either the U is different, or maybe they are even not. They're gonna see. Oh, yeah. Yes. Exactly. Yeah. I mean, if you see here, U D U minus 1 U D dagger U. Yeah. That's exactly. U minus 1. Yeah. Exactly. Yeah. Any other question? Yes.
Would also work for the SVD if it's the same.
Oh my God. SVD. I use them. Yeah, but okay, but then you will have the same matrices, or? No, these I'm not sure. Sorry? Exactly, yeah, exactly. This is exactly what I want to say. So SVD is a special case. So this is exactly SVD for diagonalizable square matrices, or? But then we cannot calculate the exponential of a non-diagonalizable matrix, because then you have something like this times something like this, and this is, or if this like this, then we cannot calculate e to the square doesn't exist. Yeah. Any other question? Yeah.
It's not diagonalizable.
No, actually we can, but then you have to do basically the. Exactly. Yeah, absolutely. But the exponential is defined by, that's why I told less special case. Or this very special case is diagonal, then we know straight away how to do. The less special case this. Otherwise, in theory, you have to really take the infinite sum. In practice, maybe there are other tricks. I don't know about that. But yeah, I probably, if you put it in Wolfram alpha, then it just crashes and doesn't give you any answer. Yeah. Great. So any other question? Okay. Yeah. So yeah, tensor product you covered more in detail in the lecture. So we are doing a recap and yeah, just a more introduction to the exercise. So the idea is we have a, so for example, 2 qubits or 2 particles, 2 Hilbert space, and we want to study the system as a whole. So this is defined as the span of with our actually here you write like this. A as an element of the Hilbert space and A element of the respective Hilbert space. So yeah, as a small recap, how can we calculate these beasts? So if we have C equal to alpha 0 plus beta 1 and the psi equal to gamma 0 plus rho 1. And here I can add that everyone is element of A and B. But many times we leave this away. Okay. What is the tensor product of the two? The idea is kind of so intuitive. Alpha, so the first coefficient here, we write it in the like vector notation. Vector. Alpha times in the vector representation beta gamma rho. And this is like an absolutely non-elegant way of writing it, but this is like to see, okay, I take the vector representation of this and I multiply it with the first coefficient. I take the vector representation of this and I multiply it with the second. So like the real result, so it's a vector, so writing a vector inside a vector is absolutely not nice, will be like this. How do we write it in Dirac notation? Dirac. This will be exactly A0 tensor product gamma 0 plus rho 1 plus beta 1 times gamma 0. Here I will have a B and B plus rho 1. And then here I have a tensor product. I do kind of a multiplication, as we know, like alpha gamma 0 a tensor product 0b. And then I take this coefficient, I multiply it with here, and so on. So this is a special case in which it seems that the Dirac notation is way more lengthy and takes more time. But in general, it's actually very efficient to apply operators and things like this. I think you saw already in the lecture, and you will see in the exercise. It's very good to know both of the representation, but bear in mind, Dirac notation is the best way to go. Yes? Yes, genau. Yeah. Sorry, thank you. Yeah. Yeah, this is also something many times you really don't write, because if you always put A in front, then you leave a weighted base. But of course, if you do it, that's very great. You never do a mistake. It's absolutely amazing. Yeah. What about matrices? So let's put it like here. For a matrix. So let's say we have a matrix O and M. Okay, and O acts on my inverse space relative to A, and M on my inverse space relative to B. So vector, which is actually here is more matrix, but representation, we would have that O tensor product M. The idea is basically the same. So here, let's say O M are 2 by 2 matrices. I will have that is my 1, 1 coefficient. So if I write here O is equal O 1, 1, O 1, 2, O 2, 1, and O 2, 2, times my matrix M. Here is O 2, 1 times my matrix M, O 1, 2 times my matrix M, and O 2, 2 times my matrix M. So here, this is to see an analogy with here. Or I take the first coefficient and I multiply it by the vector. So every coefficient of this vector is multiplied by my first coefficient, and same for the second. Here, the idea is exactly the same, only I don't have a vector, I have a matrix. I take the first coefficient and multiply it by every vector, by every coefficient of the matrix. So this is a 2 by 2 matrix, and this as well. So in total is a 4 by 4 matrix. How here this is like will be O11 times M11. Second element is O11 times M12. Here I will have O21 times M21. O21 times M22, and so on. Is that clear? So yeah, also tensor products sometimes is like a bit tricky, but also again, Dirac notation separates the two, makes everything very easier. For example, let's put it like this. Yes. Now, suppose we have tensor product M applied, and here we always can write A and B, psi tensor product phi on A and B. Here we can see that in vector representation, we first have to calculate psi tensor product phi. And then this will be a vector. Then calculate O tensor product M. And this will be a matrix. Or matrix. So here I have to do 4 multiplications. Here I have to do 16 multiplications. And then I have to calculate this matrix. So psi A times B. And this will be 60 times 4, or yeah, I think, yeah, 60 again times 4 multiplication. Or 4 by 4 times 4, yeah, 4 times 4 times 4 times 4 multiplication. Yeah, so this is the vector representation. For the Dirac, this is exactly like equal O times psi A times M. Sorry, this is not tensor product. So I apply my operator, which acts on the Hilbert space A, to the state which is in the Hilbert space A, and I tensor product it for the operator which is in my Hilbert space B, and I let it act on the state which belongs to this Hilbert space. So I don't have to do all of this story of matrices and coefficients and everything. Yes? Yeah, exactly. So because I have, yeah, this matrix has 60 elements, and for each element I have to do a multiplication. Okay, this is like, this is not just to give a rough idea, but yeah, this is a 4 times 4 matrix. Okay, and if I multiply this 4 times 4 matrix with a 4 vector, I have to take each row which has 4 elements times one of the element here 4 times. So this is why it comes from. But yeah, this is absolutely not very relevant. It's just to tell here it's way more straightforward. And it's very separated. You can see what belongs to A, what belongs to B. Of course, you don't have the mismatch, but it's usually quite clear. And I mean, this is a very simple system, two-level systems. But as far as you go a bit bigger, if you have 3 spins, this will mean you would have 16 by 16 matrix, which is 8 by 8. Sorry, yeah. Yeah, to 8 by 8, which is already bigger. Yeah. So I have 4. No, this is 4 times 4. Yeah, you're right. Yeah. Okay, but in total, because before we had already 4. Yeah, this is for the last 4 times 4. Yeah, this is. But again, this is like only to give an idea. Tensor product in vector notation, the only way it's nicer to see is, in my opinion, is the very first example, when you have two states that you will combine, and afterwards it's kind of a mess. So now I realized that I did the break completely wrong. Yeah, sorry, I'm used to the Eggenberg times. Yeah, okay, that's great. I will. That's why I didn't go that farther. Yeah, but this is absolutely, sorry for missing up this. Absolutely, yeah. I asked myself why I didn't go that far. Yeah, great. Yeah.
So in general, we say that when we have like two systems like A and B, so if the components of A always only act on the components of A. Mm-hmm. So even if we were to reverse like the psi and the phi, so we would have the b vector tensor with the a vector, would that still give the same result? If we were to change the order of.
Yeah, this is exactly the exercise of this week. And that's what we are looking now. Yeah, exactly. That's great. Yeah, thank you for the question. And yeah, now I feel good. So now we have exactly, so how we draw it on a circuit. So this case, so let's call it star case. We will have a psi, this, and then I apply my circuit O, and here apply my M, like this. Do we agree? So here we have okay, kind of a, yeah, mu equal, we can, yeah, let's write it like, or no, this, we can this. And we take our state mu, mu is equal psi A tensor product phi B. Yeah. And the two operator acts on very different state. Now we saw the lecture, the application, for example, of different circuits. I am terrible with the pronunciation. So you probably maybe first apply a O and then an O prime and so on. But also the application at different times. So we have if we have again our mu here, and then we have oh, now I call them with other letters because it doesn't matter anymore. Like also to notice that it's a different example. Okay, and here, so these we can kind of interpret it as time. So this is a sort of time axis. Why this? Because these show that I first have my mu. Oh, actually it's an eta, this an eta. Then I apply U on the subspace of Hilbert space A. And then I apply my V to the subspace of Hilbert space B. Okay, and now how can I write it as as an operation, as we saw in the lecture? Anyone has an idea? So I start at the beginning, I have my eta, my state. What do I do afterwards? Or how can I write the operation 2? Yes? Okay, yeah, that's almost correct. That's great. So the fact that we put it before, this is very important. That's perfect. Yeah. 1 beta. Okay. So very important. Remember, this time axis on calculation is the opposite. Okay. So this is my kind of 1. This is my kind of 2. For the 3, what do I do? Exactly the same, like kind of exactly, because I have V which acts on B, so I have V beta tensor product, the Hilbert space A. There is nothing changed, so I have an identity matrix, and here I can write maybe with brackets, which is maybe a bit more elegant, like this. Okay. Now, oh, okay, right. Oh, we can actually go here. Yes, let's do like this. Yeah. Great. So now if we have the same eta, but this time with this sketch. We will have again kind of a 1, 2, and 3 phases. Okay, so here we will have our eta, and then we first apply this, okay, and afterwards this. This means we have to swap the order. We first have 1A tensor product B beta, and then afterwards the U gate beta. Okay. Now exercise 2 is show that two are equivalent. This means if I apply the gates on this order, I get exactly the same result as if I apply the gates in this order. Yes. Ooh. Thank you. Yeah. Thank you. And also, plus, it also shows that. So to show is also that if you apply in exactly this way, you get the same result. So that this is end is equivalent to UA tensor product file B eta. Okay. It's probably you tell, okay, it's not really a very amazing property, which I can agree with, because yeah, I mean, here is very separated. So the properties go maybe with a bit our intuition, which is our intuition is usually classical. Okay, what is different is if we have operators which act on both of the two. Okay. If we don't have these two separated anymore, then everything changes. And this is where quantum mechanics, usually we cannot understand it anymore. We use it, but we don't really understand it anymore. So yes, now I can quickly look at what's reasonable to do. Yes. Okay. Good. And yeah, this is a property of tensor networks, which tensor products, which you show in the exercise class, and it's to see as something you will always have and can use for exercises, for the exam, and so on. Okay, it's not just a side exercise. If you don't manage to show it, it's absolutely okay, but use it from exercise sheet 3 on. Yes?
So, for example, like in the top left corner,
Yeah.
are we allowed to use directly the same as VA times VB? Or, you know,
No, these you also have to show.
Exactly.
Exactly. Yeah. Yeah. And how to show, like, yeah, wait, maybe I'll give you just, it's pretty, I mean, tedious. It's not difficult, but it's mathematic, but it's like, yeah, if you take like UA, like the most general operator, so general operator operator, and then psi A as sum over L of the psi L in CL basis. This will be a sum over the basis states with a coefficient phi b, same, sum over k of some beta c k b, and so on. Yeah, as alpha L, thank you. Yeah, alpha L and beta K. Yeah. Okay, and same operators. Yeah, you write them as also UA will be a sum over L prime of alpha L prime of L prime. Upside, sorry. Yes. This is a general, I'm pretty sure. Yeah. Or if, yeah, it's, it does actually with a unitary, what can you don't earn any information or no, it's a general. Yeah. Of course, in quantum mechanics, usually, no, actually, no. Time evolution are unitary, but gates are not unitary, or not all of them. Yeah. So the general, if it's unitary, it doesn't help you at all, I think. I mean, yeah, you have some constraint in the coefficients, but, and don't worry, I mean, you can show us your exercise once you will compare it with the solution. If you just assume something more than what, it's not that it's wrong, and it's absolutely not an exercise which will come in an exam, I would say, because here we don't see your understanding of quantum mechanics. But the property is very important, and the fact that you just start using a little bit of tensor product, this is also very important. So yes, and in an exam, I would say if we have such a thing, then okay, actually Lydia, it's the first time I give the course, but the other courses I've gave, then we give indications, or you are allowed to use these and these, and yeah. But don't worry about the exam, it's in a while. We first have to learn quite a lot of quantum mechanics. Yeah. And great. Yeah. Yes.
Would we also, we don't know that eta is a product state, right?
No,
so we would also have to sum over the basis of
exactly. Yeah.
Space, right?
Yeah, exactly. Yeah. Eta is the general form you saw in the lecture also. Eta is so it's maybe it's sum over L, or let's write it like N of gamma N C L A I L. This is a N now, phi N H, something like this. Yeah. Great. Then yes, I can go to the next one. Now, in the last 8 minutes, we make a quick recap of projective measurements. So we have, again, like local and global operation, bit in exactly same direction of what we saw before. So a local on a local means that we project over the different configuration, for example, basis states only on the part of on the states or on the subspace corresponding to the Hilbert space A. Okay, it's like we leave if you can imagine like this, HA tensor product HB. So my state belongs to the to the two together combined, but here I leave the part which has to do with HB untouched, and I project with respect to a state K on my part A. Okay, for example, if you have this is like probably better to leave like this. B untouched, project on A. For B is exactly the same. Okay. Oh, sorry. This is A identity on A. B K. And the global is just a combination of two. So exactly what we saw for P, A, K, and P, B, K over my multiple of over a state K. So what can we do? Also, why are projective measurements so important? For example, if I have a circuit and I do some operation after initial state, then some operation in the circuit, I want to know what is the final state. Okay, and in the example of qubit, we have the 0 and 1. So I want to know what's the probability of the state of being in 0, or what's the probability of the state being in 1. And how can we calculate it? This is like, so the probability of P, A, K, so that the state is in this, will be, so if eta is my state of exactly this operation, so the tensor product B of mu eta, so eta like this, and this simplifies as how can I write? Yeah, like A for an eta which is equal psi A tensor product phi B. We really have only to act on this part and this state, because the identity acting on a phi B is phi B, and the inner product of phi B and phi B will be exactly 1. So here we can really forget about the rest of the part, which is actually makes intuitively sense, because we project only on the Hilbert space corresponding to A, we leave the Hilbert space corresponding to B untouched. Is there any question here? Okay. And yeah, for B is exactly the same and similar for B. If you have here a sum, eta is a sum over multiple states, then the principle is again beat the part corresponding to the Hilbert space B, stay untouched. You have to then apply the operators to the sum of states, which you will do in the exercise 3 a lot. And as a last comment to the here, what is the final state? So the state after the projective measurement. So we will have psi k or eta k, psi k will be the projector applied, and here again, applied to my state, my original state, divided by the square root of the probability of the state. Oh, wait, probability PAK. This is, yeah, always in this case. Why is this very important? You know, quantum mechanics, if we do a measurement, the state change, okay? We kind of, I imagine it like this matrix multiplication of the state, or applying in the Dirac notation my operator to the state. So if in a circuit, at some point they say, okay, we project, then we have to calculate what's my state afterwards. Because in some cases, maybe there is a eta, we apply some gates, and then we apply a C naught, for example, and then another gate. And then we do a projective measurement, which is, I think, yeah, you write like this, and here as well. And maybe afterwards, we even apply another operator. So here it's really important to bear in mind that this changed. It's not only that we measure the amplitude, our state collapsed to one of our possibilities. Great, with this, it's all. If you have any question about the exercise sheet, when you need some hints, write me an email also, or in the Moodle, but also email is absolutely okay. Otherwise, have a nice week and yeah, have fun in the lecture. I'm still here for a while if anything must be unclear.